All right, so I just wanted to give a brief introduction here into the ideal gas law. So this is basically a summary, kind of piggybacking off of what you've learned in chemistry class. All right, so how gases behave. So gases are easily compressed, right? And they can also expand and contract pretty easily with temperature changes, right? What's interesting is that most gases actually are going to expand or contract at the same rate. Liquids and solids, this is not the case. Um, Now, if when we're talking about an ideal gas, what we mean is that the gas molecules are behaving very ideally, hence the name ideal gas, meaning that they're pretty spread out. They're really not interacting with each other, let's say gravitationally. They're basically just, if they do interact with each other, it's going to be a collision. And we're going to assume that this collision energy is conserved. So we've got elastic collisions occurring. And, excuse me. So the ideal gas law, I want to kind of talk about what's kind of the idea behind it through a visual example here. So let's assume we have this deflated tire. All right. So if we start adding air to the tire, we're increasing its volume, but the overall pressure is not going to change much. All right. But once the tire is completely inflated, right, once we go from this situation to here, right, well, now the tire can't expand anymore, right? It's limited by the size of the tire. So then the pressure is going to start increasing because we're putting in more air molecules, so the density of the air molecules is increasing. And then at a certain, sorry, um, we'll also see that once the tire is inflated, we'd actually will see a temperature increase as well when we have the pressure full. Right? So this basically means that these quantities of pressure, volume, and temperature in some container of gas are dependent on each other and behave in certain ways. So the ideal gas law explains mathematically how it's going to behave. So here's one version of the ideal gas law. It says PV equals NKT, right? So here is pressure, absolute pressure of a gas. V is the volume that the gas occupies. N here is capital N, not lowercase n. There's a difference. Capital N is the number of atoms or molecules, depending on how we're analyzing the graph, the gas, excuse me. And T is temperature. And then K here is a proportionality constant. That's known as the Boltzmann constant. Sometimes this is written as K with a subscript of B. In fact, I think the AP formula sheet writes it that way. But anyway, the value of the Boltzmann constant is what's listed here below. You might want to write that down. I do want to remind ourselves of the number of moles. So sometimes the definition I just gave for the ideal gas law is not the most useful, right? We may not be able to determine the number of molecules in some container of gas. It's going to be easier to deal with moles because if we know, let's say, the mass or the amount of gas, we'll say the amount of gas in a container based on the mass, we can then determine the amount of moles. And this allows us then to kind of relate things in terms of Avogadro's number. So this is useful because commonly, so what you're probably familiar with is the ideal gas law written in the way that you see in chemistry classes in terms of number of moles. So what's basically going on here is we started with this PV equals NKT, and we're doing a little mathematical trick here where we're just multiplying by 1. But we're writing 1 as Avogadro's number divided by Avogadro's number, right? So if you kind of see here in the math, this is what we're doing, Na over Na. So we're just multiplying by 1, but I've written it this way in kind of a leading way because the number of molecules or atoms divided by Avogadro number, that's that's the number of moles, right? So that's the definition of what a mole is. So that's what we call lowercase n, the number of moles. And then uh, this value here, Avogadro's number multiplied by the Boltzmann constant, that's actually what defines the universal gas constant, R, what you're familiar with from chemistry class. So I thought that was pretty interesting. So these statements here, PV equals nRT, is PV equals nKT. So you have to choose which formula is going to be useful for whatever problem you're solving for. So what is the value of R? We can compute that if we'd like. We just take Avogadro's number and we multiply it by the Boltzmann constant, and we end up with your familiar value for the wow, have I forgotten what that's called? The universal gas constant. There we go. Sorry. But you can also write it in terms of different units if you'd like. So we typically won't be using these. We'll be using our SI units. So let's see. Now, what's particularly interesting is if you look at the both sides of the ideal gas law, if we multiply our units out, both sides are actually in units of joules, right? Which is pretty neat. So this idea, this PV, is actually related to the amount of work done by a gas when it expands or contracts. We'll be talking about that later in a lot more detail, this unit. And then on the right-hand side, again, we're going to actually talk about this next class period. This value here, nKT, relates to the amount of kinetic energy available in the gas. So we've kind of got to have the amount of work that a gas does relating to the amount of kinetic energy the gas has, which is all right. Just to kind of wrap things up, I provided a summary here. You can pause and read it, and a summary here. You can pause and read it. Thank you.